Hello, everyone. Welcome to the DASP seminar for this week. Thank you for joining us. My name is Dinesh Jayaraman. I'm an assistant professor here, as many of you already know, and I will be the faculty host for today's talk. As a quick reminder, Sadie reminds me to let you know that previously recorded talks can be found on our YouTube channel and website. And also, if you would like to ask questions today, barring any quick clarification questions, we'll ask you to hold on to until the very end, when you will have, of course, the opportunity to ask your questions. You can raise your hand in the middle if you have a quick clarification question, and I'll run down to you with a microphone just so it's recorded, right? All right, so our speaker for today is Professor Igor Gilitschenski, who is an assistant professor of computer science at U Toronto, where he leads the Toronto Intelligent Systems Lab. He's also a faculty member at the Vector Institute. Previously, he was a research scientist at Toyota Research Institute and a research scientist at MIT's CSAIL lab and the distributed robotics lab as well. And he was the technical lead of DRL's autonomous driving research team. Igor joined MIT from the autonomous systems lab of ETH Zurich, where he worked on robotic perception. And before that, he did his PhD at KIT in Germany and had a diploma in mathematics at University of Stuttgart. His current research focuses on understanding perceptual, physical, and behavioral representations for data-driven environmental modeling, as well as its applications to robotics and embodied AI. And he's the recipient of several Best Paper Awards, including at the ACC, the International Conference on Information Fusion, as well as at IEEE RAL. Very excited to hear what Igor is going to tell us today. Igor, whenever you're ready, please take it away, and please welcome the speaker once more.
Okay, thanks so much. It's a great pleasure to be here, and it is also a great honor. I have a very personal connection to the GRASP Lab. I learned about it only relatively late, but this person who you guys all might know and be very familiar with, Rosina, she was on the dissertation committee of my wife, who did her MD PhD in Berkeley. And when we were dating early on, she asked me, "Do you know Rosina?" And I'm like, "How do you know Rosina?" My wife is a medical doctor, but also a bioengineer. And so to me, the GRASP Lab has a strong family connection. I am what you could call a second career roboticist. Second career because my undergrad was in math, and my PhD was on nonlinear dynamic state estimation. And it was only by a misunderstanding that in my postdoc I became a roboticist, because I was asked whether you work on sensor fusion, and the confidence of a freshly minted PhD, I said, yes, I work on sensor fusion. And my first postdoc advisor said, great, we need people who know how to do sensor fusion. And it was really a great misunderstanding, because I worked on nonlinear dynamic state estimation, on like nonlinear manifolds, designed probability distributions, made versions of Kalman filters that were intellectually very interesting, but of no practical value in most robotic applications whatsoever. At least later they had some practical value, but at that time, not yet. So by this misunderstanding, I got my postdoc position and started working on robotics. And this was one of the robots we were involved in. And I want to show some highlights. And the cool thing about this robot is it was built completely by undergrads. It is a drone that can fly in any orientational configuration. And the undergrads, it was back at ETH, there was like a project which was called Focus Project, where a group of undergrads, not every undergrad could do it, but you had to apply to it. You could work on like this type of 9-month-long developmental project and develop like your own thing. The initial version did not fly that well, but it could already like fly with different orientations. They have a commercialized version of it that looks very different, but still has some of the inspiration. We worked on autonomous planes, so a lot was mobile robots. And the next thing we worked on was not even a robot at all, but it required a lot of the robotics research. So the VR headsets, if you want to do very precise tracking, they were using SLAM. So we had a collaboration with Google 2 VR winters ago. And I think VR is a few hype cycles away from actually being broadly used. At MIT, I worked on self-driving, and I continue now working a little bit on self-driving. And in U of T, I started working on manipulation as well. And it seems like a big potpourri of different robotics topics. But to me, there is one unifying theme, and one unifying theme is the role of human mind and of imagination. The talk today is titled after an Isaac Asimov short story, Eyes Do More Than See. And in this short story, it's a little bit like a story about AGIs before the word was a thing, because it's from 1965. There are two entities who left their physical form behind them. Sounds very familiar. And they're contemplating physical existence and the role of eyes as a way to also express emotion. And for us humans, the eyes play a very different and yet a very important role as well. They are the gateway to our imagination. And our imagination is not detached from our perception of reality. In fact, our imagination is essential to how to what we perceived in reality. And this, to some extent, was very different in robotics. In robotics, there are two flavors of roboticists, I would argue. There is the flavor of roboticists who believe everything should be solved by as much real-world data as possible. And the second flavor of roboticists believes that we should do as much simulation as possible, do then sim-to-real transfer. And although in reality we use both of those, we try to collect real-world data and do real-world experiments, and we also use simulation to, we don't want to crash the robot immediately. Deep in our heart of hearts, most roboticists count themselves to the one of the two groups, I would argue. And interestingly, this is not the case for humans. So humans, our way of imagining the world is intrinsically linked to how we perceive it. And for me, there were two moments that took this home. Like, we worked on a project at MIT where we put a car on the road and just recorded some driving, and used a very simple technique, pre-generative models, to disturb the viewpoints that we recorded. And then we used a neural network to train on these viewpoints some sort of reinforcement learning control policy. And this work allowed us then to deploy this control policy on a full-scale real-world vehicle that has never seen a human driving command. And back then, we were even using a relatively naive version of reinforcement learning. We used some form of vanilla policy gradients. I'm not even sure if we implemented baselines. So it was very naive, and yet it was possible to do lane-stable driving with sim-to-real transfer without actually having to do any domain transfer techniques. And my first take-home message for this was, okay, it seems like if we use real data and simulation not in opposition, but see them uniform as one aspect of the same thing, we can actually improve learning. And funny enough, this is exactly also how the human brain works. Like, we use real-world data to generate a lot of hypotheses about the world and to interact with the world. And if you take nothing else away from this talk, I recommend reading this book. I read it back then in the thinking that I would become a better teacher. I wanted to know how to teach better, like with from a neuroscience perspective. But the interesting aspect really about it was how it inspired, like, what in human learning really, like, real-world data and imagined simulated data don't exist in opposition. They really inform each other. And a lot of my agenda became inspired by this. Now, in robotics, we typically would want like three things from simulation. We want simulation to be useful for testing. We would want them to be useful for maybe data creation or data augmentation at the very least. And we would want this third is the most controversial, but we would want it maybe to be used as part of a policy. And in robotics there is, and has been an even bigger, now it's a smaller debate about to what extent to what extent policies should be learned or which aspect of policies should be learned. But these are the three main use cases of data curation systems. And starting a faculty position, I did not have that much of a robotic infra yet. So I started a lot with tinkering around and playing with how can we make data curation systems more controllable in one way or the other. And the main theme of today's talk that will largely be focused on perception. I'm happy to chat afterwards also about some of our other work. The main theme of this talk is if you have some sort of model, large model, generative model, what is the way to make it more controllable and more realistic? And there is really a gap in this because the video generation community, for example, cares only for realism to the extent that they need it to generate nice videos. The AI for science community cares for realism a lot, but they usually model one single phenomena because they're experts of this phenomena. And there is this gap for robotics where we need realistic data generation for a bunch of phenomena, and we need it also relatively diverse, but maybe not as diverse as in video models. So a lot of the work was inspired by this. And I want to look at what are the different tricks that we can use to make different flavors of models more controllable and to create good augmentations. We will start with some very light control signals like preference optimization and how preference optimization can be used to make video models better. And for robotics, this is by far not sufficient, but it already gives you a hunch at where we may go. We can also create some notion of preferences for robotic policies, and we will discuss how we can steer robotic policies by grading them. I want to talk a little bit about video relighting, how we can control video models for augmenting video data, how we can introduce temporal control more and more fine-grained, and how we can, if we want to edit some sort of reconstructions, again, motivated by the need in simulation, how we can localize the edits and not overshoot and edit the entire image. It was a very interesting ride working on this flavor of topics because when my students came, a lot of them were motivated by entertainment applications, and their internships were initially in entertainment. But interestingly, out of the 3 graduates that gone or are about to go to industry, 2 of them are having primarily offers or having taken jobs that are where this type of work is used for robotics purposes. And I kind of feel very confirmed that this is like very relevant to robotics. Video is currently a little bit like very, very hyped and extremely relevant to robotics, and it's moving super fast. But the problems that we face in video models is really like physical and perceptual realism. This paper is barely 1 year old, and a bunch of the problems I show here are solved already. But interestingly, the technique is still relevant. So you won't see in video models something like this anymore, where there are like limbs appearing, or the giraffe is walking not on the rope, but under the rope. These problems have been solved over the literal last months. And one approach to solving them was presented in one of our work, which is based on preference optimization. Preference optimization is a technique from language modeling where you essentially ask a language model to generate different outputs to the same prompt, because it's a stochastic model. You can do this, and then you can use this. You can use these different outputs to do some form of post-training. And there are different post-training techniques. One post-training technique is some sort of reinforcement learning, and other post-training techniques are like this, particularly preference optimization. So you typically have some sort of objective that looks somewhat like this. You maximize a reward or some sort of utility function, and your inputs to that is the model output and the conditioning that you gave to the model. And you try to constrain it to not move too far away, to stay close to the original model. So you have some regularizer term. And there is a concept of this concept of direct preference optimization has been applied to diffusion models. So where you have a diffusion model that generates images, and you ask it to generate 2 images, and you basically ask a human scorer to score these 2 images. And the human scorer would either say, I like one image more than the other, and these are basically the preference data points that we have. Now, the interesting question is, how can we apply this to video models? So what will happen if we were to apply this to video models? Well, a naive application to video models, we would ask a video model, hey, can you really generate 2 videos for us? And what will happen is the video model will generate these 2 videos, and we will ask a user, hey, which video do you think is better? And the user will give us a preference based on which video is better for the entire video. Now, both of these videos contain some failure cases. Like in here we saw briefly in the top video towards the end, there was like some lag appearing twice. And here there were all some failure cases earlier in the beginning, like this physically implausible motions in the first frame. So both of these videos have some failure cases. So if we just ask a user to rate these 2 qualitatively very different videos, we may end up with some very interesting phenomena. And the interesting phenomena is the following, that usually failure cases appear in video generation when there is a lot of motion. So if you look at basically this dance video, on the left, the bear is dancing slowly, and on the right, the bear is dancing pretty fast. And the video on the right is the one that has actually the problems in video generation. So if you just ask users rate which video is more plausible versus which one is less plausible, users will tend to rate the ones with less motion as higher, because the less motion means less opportunity to introduce failure cases. So applying preference optimization in a naive way to video models will make your video model boring. Everything will be slow. Your videos will be slow. You can't train a really fast, cool robot with it. You can't evaluate your fast, cool robot with it either. So we need to somehow get rid of this motion bias problem. So what can we do? We end up with this upvoting of slow videos and downvoting of fast videos, and we end up with the suppressed motion generation. So we want to avoid this. How can we avoid this? Like in diffusion models, there are some standard techniques that people do for all types of problems. And one type of problem is you take a clean data point, you add noise to that clean data point, and you create copies of that data point, and you use it for all sorts of stuff. And this is exactly what we do here. So instead of asking the user to rate 2 completely different videos in motion, we take one video, the same generated video, and we add noise to that generated video and denoise that video multiple times. So we end up having 2 versions of the same video. And these 2 versions are qualitatively different because we ran the denoiser multiple times, so we have a different stochastic process doing it. Still problematic in different ways and at different parts, but at least what we're getting now is we're getting now preference values for videos that have the same motion. So by introducing this trick, we get rid of the motion suppression of DPO on video. So what's happening next is that we essentially had the idea that, okay, if this is the problem, we should not rate the entire video, but we should rate the individual segments, because different segments will be more or less realistic in different ways. So the first video might be good in the beginning and bad at the end. The second video might be bad at the end and good at the beginning. Bad at the beginning and good at the end. So instead of asking the user to label only the full video, we ask it now literally to label segments, and we obtain different segment labels. Here on video 1, we upvote the good parts. On video 2, we downvote the bad parts in the beginning, and then vice versa towards the end. So This really improves the performance, and you get some really interesting results. Let's take a look first at the comparison with vanilla DPO. Vanilla DPO works already much better. There are still some bugs, but you don't have as many deformations. But you do get slow motions. And then, as we introduce the concepts of structural DPO or dense DPO, which was our ultimately presented method, you end up with much better and much more realistic motions. And the dense DPO version basically has the least artifacts. Yeah.
Partly, it felt like the way that you were starting to kind of point out the problems with video generation. It felt like maybe one of the things that was kind of important is what is the use for this video afterwards, right? Like, for example, in your dance video or something, maybe a downstream user would prefer a different dance video that had poorer aesthetics, but was clearer on which steps the panda was performing if what they wanted to do was to learn how to perform a dance or something like that, right? Like, there's like a very different set of metrics that one might employ depending on what they really wanted to extract out of the video. And it feels like in the space of video generation, it's kind of unclear what it even means to generate a good video. Whereas in something like robotics, which you're kind of motivating your work towards, things become a little bit more clearer in terms of like what we really care about, right?
Yeah, and this is a very good question. So in video generation, the thing that we're optimizing for is a happy viewer traditionally. And there is actually more recently some work that explicitly addresses this problem where people, instead of looking at making the overall video nice, just try to make the aspects nice where the contexts are involved if they want to train it for manipulation. So you actually, for robotics, if you want to use video models for robotics, you need kind of different post-training techniques. And to some extent, this is also true for AI for science models. I happen to have worked more on trying to make video models more plausible, but there is like a counterpart to that story as well. And it's like an interesting counterpart. But I absolutely agree. Like you would post-train a video model in very different ways if you want it to work for robotics. And at NVIDIA, for example, you also kind of see a version of this. The Cosmos models that are essentially also, to some extent, video models are treated still differently qualitatively than a video model that is designed for entertainment purposes. But some of the control challenges are similar. So in entertainment purposes, we would want to have multi-camera control. We also want to have multi-camera control for robotics. And I think in entertainment, we sometimes want to have different shots of the same scene. So we would also want multi-view at some point. And in robotics, we want multi-view really urgently because a lot of the signal of the training of like VLAs happens now with some sort of multi-view data. So here are some more entertaining examples. It's like you could basically see that training with this type of post-training really improves optical fidelity. The giraffe is finally walking on the rope. As unrealistic as it is otherwise, it looks at least perceptually plausible. And the bear is actually riding the bike. So you can really generate much nicer things just by properly incorporating a preference signal. Now, the only robotics work I want to talk today is about steering like robotics policies. So we have now a lot of like interesting robotics policies come out that you can use. You can download from Physical Intelligence, one of their large policies, and there's an insane amount of money going in investment in these training behavior cloning policies. And the behavior cloning based policies all share one problem. The problem that they share is that they're trained on high quality data, which is not always easy to get. But the other problem is if you only train it on high quality data, you kind of throw away all the low quality data. But low quality data is very, very informative. So the question that we tried to answer is, how can we utilize evaluation data that comes from these large models. Because after we're done training with large models, we would want to utilize some sort of negative data. One idea that we would do traditionally in robotics is to use some form of reinforcement learning, which is already hard in its own right, but with larger models, it is extra hard. So we were looking at, can we use something very simple, simpler than reinforcement learning? So we have all this evaluation data, and our idea is to develop a method that can do some sort of on-policy steering in an update-free manner. Update-free means that we don't fine-tune the original model. We keep the original model as it is because it's either too expensive to fine-tune or we don't want to deal with some complications of RL. And instead of fine-tuning the original model, we take these rollouts for which we already know which of them were successful and which have failed, and we just train a classifier. And the classifier basically tells us, was our rollout successful or was the rollout a failure? And we deal with stochastic policies. So for every given state, we can generate a big bunch of actions. So this is exactly then what we do at inference time. We can generate a big bunch of actions. And then we can use this classifier to guide which actions we choose. There are different ways to do it. Like the most naive way is we just take the classifier and we score multiple trajectories generated by the policy. A more complicated way to do it, if the policy is a diffusion policy, we can essentially do classifier guidance and add some gradient of the classifier into the diffusion process. So to give you some intuition, let's say we have this type of training data walking from a start to a goal point through two openings. Some are very narrow, some are one very narrow, one very wide. Obviously, going through the wide one will be easier to learn. If we then run some rollouts on just having behavior clone the policy, we will have a big amount of failure cases for robots that go through the wide opening. And if we introduce some guidance through the classifier in one way or the other, we will introduce a bias towards going through the easier one, which is exactly what we want because it may be easier, but it achieves the goal. And we did this on a variety of tasks. Here's some examples. We did this first of all on of course also in the usual simulation benchmarks. You can read in the paper, but you really can use this to improve like some finicky tasks. This is my favorite one: grabbing the ball and putting it into a bowl. Here's how the next one shows you how a failure case of this looks like. So there are like really intricate failure cases, like grabbing round objects is very hard. Particularly if they can roll, they can easily move away. And this type of technique, here I presented two variants compared to the unguided one is red, and then we have two variants of our technique where you introduce guidance and use some sort of best of n policies. It always strongly improves the performance of these learned policies.
Quick question.
Yeah.
So this classifier that you're training is something like a value function, right? It's like a QPy kind of value function for the current policy that's generating the transitions. Am I right to think of it that way?
You can see it like that, although we don't use necessarily any of the, RL machinery. We just train it based on success and failure.
But the reason I asked that question is that once you now start using your QPy to bias your policy's sampling, you're effectively creating a different policy.
Yeah.
And your QPy might no longer apply, right?
Yeah.
So there's this kind of danger that by guiding it from the transitions of your original policy and using this QPy, that you've actually generated a different distribution to which your QPy is no longer quite as applicable. Am I right to kind of see that as a potential?
Yeah, but at least during the rollout, depends on what nature of policy you have. If your policy is just outputting trajectories and there is no other type of scoring involved, it is not it does not make a problem in practice. What actually makes the problem in practice is that you would need this guiding classifier for each task individually, or you need to learn a classifier that can do multiple tasks, but then you again have a large-scale learning problem. I think the most use of this type of idea is if you have a giant pre-trained policy that has seen many tasks, but you want to deploy it on individual tasks and be data efficient. So this is basically trying out to squeeze the data, squeeze out all of the data that you have. The last two topics that I showed, we use very coarse control signals. The control signal essentially was, I like a video more or less, or this rollout is good, this rollout is bad. But the interesting thing when you work with very large models, and this is like where a lot of research that still uses a lot of classical non-bitter pill thinking can go, is how can we provide much more fine-grained control? Much more fine-grained control, for example, can be relighting. The student who worked on this project that we presented at NeurIPS, Kai, he is more interested in entertainment, but funny enough for this project, roboticists are asking now a lot about it because the large-scale policies are very brittle to different illumination conditions. So we want to start with a video like on the left and obtain a video that is like on the right. From a pure control perspective, this is still not perfect because here the video on the right also changed the type of cat, so it's not perfect relighting. But for robotics, for example, something like this as a data augmentation technique would not be a problem. There are a bunch of interesting relevant background works, such as diffusion render, that inspired us. Instead of going over all of this, I will maybe tell you how a naive pipeline would look like. A naive pipeline would look somewhat like this. We have an input video that we want to relight, and we have some model. In our case, it's a diffusion model, but basically you can treat it as a black box if you're a roboticist who doesn't like this type of stuff. And we have an input that basically is a bunch of environment maps that provides information on how we want to relight the scene. And if we train our relighting model like this, we will end up with a bunch of artifacts, and the artifacts will be primarily things like shadows. So this relighting model does not really remove shadows, this naive approach, because it's kind of hard to learn, and maybe it would remove shadows if we had an infinite amount of data, which we don't. And we have taken some inspiration from other work in video modeling, and in video modeling it has been shown that motion prediction can be much better in video models, in this Video Jam paper, if you additionally introduce as a supervisory signal some form of optical flow. So if you introduce additional supervisory signals that have you don't need in the end as an output. So at the very end, you would not be interested in the motion prediction that comes out here. But if you introduce this as a supervisory signal, it is a meaningful mechanism to improve also the output of the task you're originally interested in, which is the video prediction task. And we applied a similar idea to the relighting problem. And funny enough, if you apply this idea to relighting, well, the big challenge is what is the counterpart, the relighting counterpart of this. And in our case, the relighting counterpart of this was to not only predict the relit video, but to also predict albedo. And by predicting the albedo of the scene, this change alone is basically sufficient to make the bad shadows go away. So it's in some sense it feels funny because we actually make the task on the neural network harder by adding an additional output head. But by making the task harder, we also make the supervision more detailed. And this extra detail in supervision provides better gradient signals. And as a consequence, we end up with much better and more meaningful shadow generation. So you can see it here in the middle is without the joint modeling, and you see a bunch of wrong shadows as we relight, and ours get our approach where we also model the albedo as an additional output gets the shadows right. So if this is unintuitive to you, the good way to think about it is not in terms of the task becoming harder for the network, but the good way to think about it is that we make the supervision richer, and by making the supervision richer, we provide a more informative signal. This work has a bunch of interesting challenges. The challenges are finding the right data sets. So one problem is there are actually not many really data sets. We had a 3-stage data set strategy where we first used some existing small data set that has good relighting. Then we used some real-world paired indoor scenes where someone handcrafted relighting data, which was also small. It actually was the smallest that we had. It was like 1,000 scenes with 10,000 images in total. And then what really helped towards the end, where we really increased, where we increased the quality, is we used a video model to help us generate additional data. And we estimated from the video model generated data, the albedo. And that way, we use basically an albedo estimation technique as an auto-labeler for this type of technique. So it really, like, to me, I like this work in several ways. It, first of all, provides a useful real-world data generation system, but the real-world data generation system itself has benefited from a learned from real-world data labeling system. And this idea that real-world data can help us in the generation of data and realistic data, I think it is, even though it's very, very hyped now, but really the focus on realism is for what we need for robotics is still, I would argue, still underappreciated with what it can do. So here we provided illumination control. Technically, illumination control is just you control light sources. So it's like dependent on the number of light sources. Here I can show you guys some more generated videos with estimated albedo and the relit version. Now we want to go inside to go to a different form of control where we want to provide detailed guidance, and the form of control that we would want to have our models. So you guys see we're trying to go away from only text-only control. Is we want to have temporal control. Video models used to struggle with this a lot until somewhere late last year. It improved massively late last year, and our work was only one of the many works that worked on this. So if you take a video model today and you ask a prompt like this, the problem I will be showing now will not exist. But in early stage video models, you had the following problem. If you ask a video models to do a sequence of tasks, it often gets the order wrong, or it forgets a subtask. So video models were really bad at reasoning about time. And one problem that we as a community faced is how can we make them better at reasoning about time? The standard solution, bitter pill solution, is okay, more data, no problem. More data will solve everything. But the question for us is, can we do something smarter than just more data? Because actually more data is pretty expensive. So if you can substitute money with brains, you will be able to benefit. So if you try something like this on a back then state-of-the-art video model, I think here it was the Kling model, you will get a not perfect following of this prompt. So the man did raise his arms, but somehow they never went properly to the right, and at the end he just looked to the right, and to the left they also didn't go properly. So what we would want is we would really want to not just have a sequence of tasks, but we want to give the video model also a perfect temporal choreography. You know, the way a director would in a movie, or the way a test scenario generator would in a robotics company. We would want the models to be able to tell this is happening for that amount of time, the next event is happening for another amount of time, and so on. And this is exactly what our work did. We literally created a system where we can provide text prompts, a general prompt for the video, then individual prompts for sub-events. And these sub-event prompts would basically control the video at different phases of the time. So first we would raise the arms up, then lower them, then go to the left, and then go to the right. And for everyone who has thought, okay, now everything is better lessened and all the scenario-specific thinking is over, there is some good news, because it may, even if this were true, the scenario-specific thinking is just not over, it's just somewhere else. And in our case, the somewhere else was the attention mechanism. So what we did is we changed the way attention mechanism worked for these video models by introducing what we call a temporal cross-attention mechanism. And the temporal cross-attention mechanism, for all of you who know a transformer, it's a little bit an intimidating slide, but it does a very simple thing. Instead of providing just one text prompt, we provide now multiple text prompts with temporal information. So we have a text prompt, and we have for each text prompt a time span. And this time span is used to manually bias the attention towards a certain time. So for the frames that are generated covering the first 2 seconds, we would basically use the time span to manually bias the attention mechanism at looking at the first text prompt. For the next frames, we again would manually bias the attention mechanism to look at a second text prompt. The technicalities of this is that we changed a little bit the way rope encoding is integrated into cross-attention module. And there was some mathy derivation, but the bottom line is that it's essentially a Gaussian filter applied on the attention mechanism. And it basically allows different events to only be relevant for different points in time. And that way you get some really good controllability, where you really can have detailed temporal control over time. And this you can generate really funny videos from this, like cats walking and re-entering frames. And you would always get this knowledge that it will happen at exactly the times you wanted, which until then was not possible. Now, finally, we want to also have some spatial control. And the topic of spatial control is a giant topic in and of its own right. I want to show one example work. If you take some sort of image generation or image editing model that is based on a single prompt, you will end up with a very interesting problem if you do a naive approach. Let's say we take this image and we ask an image editing model to add a mustache to this image. Arguably, what will happen is that the image editing model might come up with an image like this. And the problem is that this is not what we want. We actually would want an image like we see here on the left. We don't want the entire image to change, but we would just want a mustache to be added to, and everything else remain the same. The problem is that some of the image editing models are just fine-tuned image generation models, or trained in a way that relates much more to image generation. So the research problem that we tried to solve is, how can we take image generation models or image editing models that are over-eager to edit the entire scene, and make sure that they only edit the relevant parts of the scene. Let's start with this simple example where we want to turn the owl into a falcon. Again, I mentioned this idea that we can use some sort of noisy version of the original image, and use this later on for some sort of analysis. And this is exactly what we're doing here. We take the original image, we obtain a noisy version of the original image, and we do this in 2 ways. We do this initially with the full edit, where we tell this instruct pix-to-pix model, which is an image editing model, to turn the image into a falcon, and obtain the noise map of this. And we do the same thing without editing instructions. And this is where the interesting part happens. So one is the noise corresponding to the edited scene, and another one is corresponding to the non-edited scene. And then we can look at these 2 noises and take the difference, some sort of normalized difference of those 2. And what will happen is that even the over-eager editing model actually inherently knows that the area that needs to be edited is the area where the owl is. So it will want to edit much more, but it will know that the area it has to edit is actually the owl. So the thing that we're essentially doing is we can use this to create a relevance map. And we consider this to be the relevance map that we want to edit. And from this relevance map, we can apply some thresholding technique, maybe region growing. You can think about a lot of clean image processing cleaning techniques, and we obtain a relevance mask. And this relevance mask can then be used for mask-guided editing. So instead of editing now the entire image, we can use this mask to tell the model, constrain your editing only to the masked area. You can even do interesting things with it, like fine-tune it so that it gets edges right and things like that. But the bottom line here is by introducing this idea of masking for images, we obtain now edits that are spatially very focused on the area that you actually would want to edit. And we obtain those in a data-driven way. So no human labeling is needed to actually tell where the edit needs to happen. Instead, we amplify the knowledge that the model already has and tell the model, hey, the areas where you're uncertain about doing many edits are actually areas where you shouldn't be doing these edits. And you get a lot of really cool and interesting editing results. The fun thing about it is you can also do it for nerves and Gaussian splatting. You do essentially the same thing. You have some image that you want to edit. And now the image is not one single image, but it's a set of images that you later on use for scene reconstruction. So you can do this relevance map and relevance mask calculation for each image individually. And then you can train a nerve on this and obtain a relevance field. So you now have a nerve that tells you which areas are more relevant than others. And from this relevance field, you can essentially have a rendered image where you perform relevance guided editing, as I just shown, on a per image basis. You perform it now for each image in the nerve individually. You can use some form of consistency losses. But to make a long story short, is you end up with the ability to optimize both fields jointly, and finally you can start from this bare statue and using this relevance guided editing create a new field, the relevance field, and then finally turn this relevance field into a new nerve that actually has a panda, although this is a pretty scary looking panda, I have to admit. But it is the relevant part for us at this point is that this panda is physically is across views consistent and somewhat photorealistic. And in that particular part, the scary part is on purpose, because the way we edit is we don't want to change the geometry. We only want to change the surface view. If you turn the bear into a grizzly bear, it looks much more realistic. So this type of approach helps more with changing textures and editing textures while maintaining the 3D structure on purpose. So what is the main takeaway for me from working on this type of work? I would argue, as we have heard a lot, that bitter lesson will make us all unemployed and nothing is as it seems to be. I would argue, in some sense, even if it is true, it may be true somewhere in pre-training, but the moment you want to do something interesting with large models, you actually have all the nice mathematical and geometric reasoning back at play. To put it simply, control techniques and steering techniques and post-training techniques, they all love some sort of and have a need for some sort of geometric or task-specific considerations. And this is kind of even true for language modeling. If you ask in a language model company, hey, who are the cool people in your company? Well, everyone will say my own team is the coolest, but then they will say probably the post-training people. And if you look what the post-training people actually do, they do a lot of task-specific either data curation or task-specific reward shaping or creating some verifiable reward systems. And I feel like a version of this is coming to computer vision and to robotics. And with that said, I think there is a lot of very interesting work to do in the controllability space. This work today has been done by this set of amazing graduate students, with the exception of Ashkan. He graduated already, so no student anymore. And yeah, you should check out some of their other works. They have been doing a lot of cool works. And thanks for your attention.
Thank you, Igor. Questions from the audience?
I thank you for the talk. It was really nice and very kind of very insightful to see what kind of techniques we can use to adapt these models. So I think that you were mentioning that one thing is knowing like the actual like geometry and putting in these biases into post-training. But I think another big aspect is trying to figure out what are actually the things, how do the pre-trained models actually tick, and maybe leverage some of the thinking steps that they might be taking to generate the outputs. So can you speak a little bit about, if I have a given, like let's say inductive bias that I want to put into my model, is it how compatible will it be with the specific model that you're using, given how it potentially learns to solve the task in pre-training?
So say it again, if you have a specific, what did you want, data point that
I
you
mean,
want?
yeah, so it's not that any given inductive bias will work well in your pre-trained model, right? And so we need to also figure out what are the maybe inductive biases that are better to incorporate. And for that, we have to understand maybe better what are the thinking steps that the pre-trained model might take. And maybe you can speak about that, or whether you have gained some intuition about what are the specific inductive biases which work better versus others.
Yeah, I'm no pre-training expert. Yeah. One thing that I learned about pre-training is, and that's actually a very interesting aspect also across domains, is that in pre-training, the data quality matters a lot. So for example, one of the reasons that companies like AI2 can train at a much smaller budget than OpenAI could train a short time later, relatively high quality models, is that they really invested much more time in making the pre-training data much better. And a lot of thought went into how can we create better labels for pre-training data, particularly for vision language data. So in pre-training, I feel like data quality matters a lot. And it matters that much, actually, that data quality and the way it is obtained is considered the actual secret. I remember talking to a friend who works at a language modeling company, and which was still releasing very detailed technical reports. And I asked them, don't you fear for your competitive advantage by releasing the detailed technical reports? And the answer was that our technical report, actually, it's not a publication, and it would not rise to the bar that we hold in publications, which is reproducibility, because we don't release one of the most important things, which is how the data set is curated. And we observe that the data set curation has an extreme impact on performance. So I think particularly for pre-training, you would look a little bit more on how data is curated, and a lot of time is spent on filtering and synthetic enrichment for pre-training data. And this is what is happening in pre-training. So pre-training is a little bit less domain-specific adaptations and a little bit more of just getting very interesting and very useful training data.
Yeah, just as a follow-up, I mean, my question was more about the post-training, like what is the specific inductive bias in post-training that that works better than other inductive biases, like if there's some intuition there?
I think this is to some, particularly for vision and robotics, this is an open research question, I feel. Like for individual tasks, we might know it. For example, the temporal control problem is much easier if instead of using just generating the full video scene with one diffusion model, you use some sort of autoregressive generation. But in general, because we want a lot of control affordances, for some of the affordances, this may be very affordance specific. And I think this is like the actual interesting research question now. Like once you're done with pre-training, once you have good data quality in pre-training, for which tasks do you need which type of inductive biases? At least to my understanding, this is like more, still open. For some tasks, it's easier. Like in relighting, there will be not as much work to do anymore. It is already pretty good. And my relighting student who worked on relighting, I think he stopped working on relighting because now for robotics, there is the challenge of making it multi-view consistent, but otherwise it works already quite well. For other tasks, I think it is more open. And I think particularly for robotic interaction and getting like the physical interaction precise, the video model community does not care to that level of precision as we do care.
Thank you, Igor.
Thank you so much for the talk. I had one question about your editing pipeline at the end. So what was the motivation in using this pixel-to-pixel model and then doing the difference to determine what the target region for the edit was, as opposed to training something explicitly? So I could imagine a world where to build this mask, I just train a model where I ask it, here's a prompt of what to edit. Here's a properly edited version. Learn to regress the mask. Is that something you considered, or?
Yeah, so the motivation for that is that I would argue that the approach we took is easier because we already use the knowledge that is there in the model, right? So we don't need to generate a lot of training data where we have the perfect edit. We just amplify what the model's knowledge is. If you have a lot of data and time, you would maybe do even better by training. But in our case, the motivation was we already have the knowledge in the model. We just need to make the model a little bit more confident about its knowledge.
So Igor, you mentioned at the beginning of the talk that there are these potential use cases for video models and robotics that people are considering very actively, and indeed there's a lot of excitement around doing data creation, data augmentation, potentially even using it for planning. Do you feel like we have insights about like what we need to improve about world models or about video models in general for them to be useful in these various cases? Like, are there actually different desiderata for these different use cases, or in general, like a application to robotics, is it kind of, do we have a sense of how much just kind of continuing to chase improved video models, broadly speaking, is going to help us? Or do we need to start kind of switching tracks to be more specialized to robotics use cases? Traditionally, the way that people have thought about simulators and robotics is often that, we want to kind of cut some corners in the simulation. We don't want to really, have the highest fidelity physics models for simulating every possible phenomena, because most of it doesn't matter, right? And it feels like that kind of thinking has not yet been systematized, at least in the video modeling kind of community. So it's kind of a cloud of thoughts, and I was just hoping that you'd maybe help make some sense of it.
Yeah. So I like the robot learning community seems to be most excited about these world action models where you use the video model as a backbone for the policy. I actually don't think that this is the most relevant use case for a practitioner. Like if you look at self-driving car companies are a little bit a precursor for what might expect us in manipulation. And they use this type of models primarily for testing, or like the reconstruction is used primarily for testing. And I remember even discussing with Raquel about it in Toronto. We started talking about it, and I'm like, yeah, people are so excited about it for training. And she was like, yeah, but for us, it's very important for testing. because you can get very interesting data-driven evaluations. So I think for real-world applications, this is like a little bit by research an undervalued use case. We would want it a lot for testing. Data augmentation is also a little bit an undervalued use case. And now coming to the actual policy learning part, the big problem of video models is that we don't need to generate image frames just to generate our robot's action commands. It just feels wasteful. And if you want to have your robots do cool stuff, then and cool stuff fast, then it's just also a waste of compute that you might need otherwise. So there has been now, I think just a few days ago, a recent work, I think it was called Fast Video Action Model or World Action Model, where the video is only used during training. And because it has video is useful, it has informative physics knowledge. And I kind of buy that argument. But yeah, I think the next big step will be how can we get, even if we use a video model as some sort of backbone for a policy, how can we get rid of video generation at test time? Because we don't need to generate we shouldn't need to generate future frames just to get actions. And we shouldn't need to have a model that is very good at generating images of nice textures just to get actions for a robot. So I think this is like a big challenge. We want to have the physics knowledge from video models, but we don't want to have all the pretty knowledge. There is another big problem with video models. There was another recent paper where a video model was linked to a physics simulator at test time, and the physics simulator helped guide the video model. And the interesting thing is that with this idea, the video model performed better than without the physics simulator. And this is actually sad news, because one of the motivations for video models is that if we use a data-driven model, it will perform better than a handcrafted simulator. But because it has to simulate so much, it is still at a stage where it has not beaten just out-of-the-shelf physics simulators, which, by the way, is true for AI for science. In AI for science, there are models that, in some sense, are superior to handcrafted simulators. But in video, this is not true yet, and it might be a while until it will be true.
Any more questions from the audience? If not, then thank you once again, Igor. Let's thank the speaker.